Right. Well, thank you very much for the invitation and also for sort of, being involved with this conference. And I'm very sorry that I wasn't able to be there in person. And, I think I really missed out. I will talk about joint work in progress with James Newton. Hope you can see this. And the idea is to discuss modularity of, yes?
Is it possible that you write a little bigger?
Write bigger. I will try, yes. All right. And the idea is to consider sort of what can be said about modularity of elliptic curves. And in fact, I will restrict myself to imaginary quadratic fields. And I want to just remind you what is known about modularity, first of elliptic curves over the rational numbers. So this is a result that goes back to work of Wiles and Taylor-Wiles. And was completed more than 20 years ago in work of Broy, Conrad, Diamond, and Taylor. And this says that if you have a rational elliptic curve, then it's modular. And well, this can mean a couple of different things. But the way that I want to think about it in this talk is there exists a cusp form F, which has weight 2 and level gamma naught n for some integer n, and which is a Hecke eigenform. So an eigenform for all the Hecke operators for primes that do not divide n. And such that the following relation is satisfied. So the eigenvalue of F under TP is equal to another quantity that's AP of E. So this is the eigenvalue of TP on F. And this is P plus 1 minus the number of points of the elliptic curve viewed over the finite field with P elements. And this happens for all good primes, which are the primes that do not divide the level n. Right, and this modularity, for instance, implies the Hasse-Weil conjecture for the elliptic curve. So it tells you that the L function of the elliptic curve has analytic continuation to all of the complex numbers. And this is something that you need in order to, say, formulate the Burton-Swinnerton-Dyer conjecture, since that concerns the order of vanishing of that L function at 1, where a priori this L function was not defined. All right, and so this is kind of the, kind of gold standard in terms of modularity results from 20 years ago. So I want to give you an outline of the proof in 4 steps. And then afterwards, I will talk about what can be done over real quadratic fields, where it's also a known result that all elliptic curves are modular. And then I will discuss the case of imaginary quadratic fields, which is the work in progress that I mentioned at the beginning of the talk. All right, so the 4 steps are the following. And I said something about modularity. So yeah, we want to think about it as an equality between these 2 sets of numbers. So in other words, we want to say that the sort of the system of Hecke eigenvalues attached to F also corresponds to this elliptic curve. It comes from an isomorphism on the 2 Galois representations. The Galois representation attached to the modular form F and the Galois representation that you see on the Tate module of the elliptic curve. In the case of rational elliptic curves, you can formulate modularity more geometrically by saying that you look at the modular curve of level gamma naught n, and you look at its Jacobian, and there is a quotient of that Jacobian that you can identify with the elliptic curve. So there's a geometric way to think about modularity over the rational numbers. But when you change your base field to a real quadratic field or something more general, you can't always expect that the geometric result would, or you can't always expect to be able to prove the geometric result. So in some very special cases, maybe you get something. But the general thing that we're going to be looking for is sort of this kind of equality that I have here, and which really comes from an isomorphism on the level of the associated Galois representations. Okay, so the outline of the proof, first step is you want to prove a modularity lifting theorem. And this is something that sort of gets used for proving modularity of Galois representations. So we consider rho bar EP to be the residual Galois representation that you see on the P torsion. So the Galois representation that you see just on the P torsion of the elliptic curve. And this is valued in GL2FP. And you assume that this is both modular and has large image, which I'll make precise sort of what kind of large image one means later in the talk. Then the characteristic zero representation that you see by looking at the whole Tate module of the elliptic curve, which is again a representation of the absolute Galois group of Q. It's two-dimensional, and it's now going to be valued in ZP or in QP. And then you show that this is modular, right? So the modularity lifting part is you assume residual modularity, and you assume some condition on the image of the residual representation. And then you prove the modularity in characteristic zero. And the key to this step is to use the so-called Taylor-Wiles method, or something that's maybe also known as patching, the patching method. So Taylor-Wiles patching. And the idea here is to sort of construct a family of Galois representations that lift your fixed residual one by varying the tame level. And you also have a similar sort of p-adic family on the side of modular forms where you're also varying the tame level. And then rather than matching these two individual points, you match that sort of are in these families, you match the whole families. And this patching method guarantees that you can construct sort of nice enough families where sort of you can hope to be able to match them. Okay, so that's the first step. The second is residual modularity. So one of the assumptions in the modularity lifting theorem is you had to start out with the residual representation that was modular. And so in some cases, you can do this. For instance, if you work with a small prime. So for instance, if P is equal to 3, then the residual representation on the 3 torsion can be shown to be modular using the Langland's tunnel theorem. So this is because this representation is going to be valued in some, well, in GL2F3. And this is solvable and also admits a faithful two-dimensional representation over the complex numbers. And such a solvable representation is known to be modular by sort of known cases of the Artin conjecture. And one subtlety here is that this Langland's tunnel theorem gives a priori just a weight 1 modular form whose associated residual mod 3 representation is isomorphic to the one that we have, rho bar E3. And there's an extra step where one needs to construct a congruence from weight 1 to weight 2, because we were saying that being modular really meant that there was a weight 2 modular form attached to our elliptic curve E. So there's a subtlety about going from weight 1 to weight 2. Okay, so using this, if you know that your image on the 3 torsion is large, well, then you also know it's modular. And so your hypothesis in step 1 is satisfied. And so you can show that the characteristic 0 representation is also modular, and then you're in good shape. But you can't always guarantee that the image of the Galois representation is large on the 3 torsion. So the next thing is that one can also study the mod 5 Galois representation, and one can show something using a so-called 3-5 modularity switch. And the idea here is to find an elliptic curve, a different one, which is also a rational elliptic curve, such that the mod 5 Galois representations of these 2 elliptic curves are isomorphic. So for instance, showing that one of them is modular will tell you the other one is modular, and such that the mod 3 representation associated to E prime has large image. And the way that one does this is one studies the twist of the modular curve with full level 5 that is attached to our original elliptic curve E. This is something of genus 0, and it's not too hard to show that it has a rational point, and then it's isomorphic to P1 already over Q. And so it's relatively easy to find lots of rational points, in particular rational points that have this extra property of large image mod 3 using the Hilbert irreducibility theorem. All right. And then you're just left with the last step, which is understand the exceptions if your image mod 5 and your image mod 3 are both small. So step 3 will give you modularity, but residual modularity, mod 5. But in order to prove the modularity lifting, again, you need large image. So the elliptic curves to which these 3 steps will not apply are the ones for which both the mod 3 and the mod 5 image are small. And so understand exceptions. And so, for example, if both of these representations are reducible, so their image factors through a Borel subgroup, but then, so that's just one example, but the way that you can deal with these particular exceptions is that this elliptic curve will correspond to a point on X in, I guess, to a point in X naught 15 of Q. So you have a line on the inside the 3 torsion, that's Galois stable, and a line inside the 5 torsion, that's Galois stable. That's exactly going to give you a gamma naught 15 level structure. And so you will get a rational point of this. And now this is an elliptic curve with Mordell-Weil rank 0. And it has finitely many rational points. In fact, it has 8 rational points. And you can analyze these by hand. Basically, 4 of them turn out to be cusps. The other 4 of them end up corresponding to isogenous elliptic curves. So there's just one thing that you want to understand, and the conductor of that is not too large. So you can prove sort of by hand that it's modular, for instance, using the Folting-Serre method. Okay, so this is the structure of the argument to prove this kind of modularity theorem for elliptic curves. So now I want to mention, what happens if you change your field from Q to some extension. And as I said, I want to consider the real quadratic case and then the imaginary quadratic case. So in the real quadratic case, this is a theorem from about 10 years ago of Freitas, Lehung, and Zixek. So let F be a real quadratic field and E over F an elliptic curve. Then E is modular. And I won't say this precisely, but let me just mention. So there exists a Hilbert modular form of parallel weight 2. Which has system of eigenvalues. 2 with system of eigenvalues, basically something like this. So for each prime of F, you can consider this kind of quantity, AP of E. Right, so this is what modularity means for the purposes of this talk. And one thing to say, so a modular form, let's say F again. So F would be a function on 2 copies. So a product of 2 copies of the upper half plane modulo a congruent subgroup that is contained inside SL2 OF. Right, so that's sort of what a Hilbert modular form is. Another way to think about it is it contributes to the cohomology of the associated Hilbert modular variety. And it would contribute in degree 2, H cross H mod gamma with coefficients in C. And this is by sort of some version of the Eichler-Shimura isomorphism. Right, so this modularity becomes sort of looking for the right system of Hecke eigenvalues in the cohomology of this Hilbert modular surface, which turns out to sort of have an algebraic structure, and at least the associated Galois representation to our Hilbert modular form can be constructed by looking at étale cohomology, either of this surface or maybe of some related Shimura curve. Okay, and to prove this theorem, one uses a similar method. To theorem A, so this would be, so maybe I just go over the steps that I outlined, and I sort of tell you, I don't know, what's different. What's different in the case of a real quadratic field? Maybe I'll use, let's say, blue, for adding what's new in the real quadratic case. So, I mean, you still want to use this Taylor-Wells method to prove a modularity lifting theorem. So you assume your residual representation is modular with large image. You want to prove modularity lifting. It turns out sort of it's more subtle to do this over a real quadratic field, or even when you do DL2 over a totally real field. And sort of that one needs improvements to this modularity lifting technique that were introduced by Kisin. And the key there is to really think about your families, so that you construct, say, of modular forms by varying the tame level, as living over the local deformation ring at P. So it's really important to sort of work with everything over the local deformation ring at P. And then you see that sort of the geometry of that deformation ring determines whether you can prove your modularity lifting theorem or not. So in this case, you want to work in the Barsotti-Tate case. So that's because, I guess, that's what the Galois representations attached to elliptic curves are. They're going to be crystalline and with Hodge-Tate weights 0, 1 for each of the two embeddings. So let me just say MLT in the Barsotti-Tate case. So crystalline and with Hodge-Tate weights 0 and 1. And one sort of works over Barsotti-Tate local deformation ring at P. Okay, then another thing, so one can still prove residual modularity using the Langlands tunnel theorem. But in order to prove, to do the sort of handle all the cases, it's not enough to just do the 3-5 modularity switch. That's because the exceptions, for instance, a lot of exceptions are going to be parameterized by the base change of this curve to your real quadratic field. And even if this has more del V rank 0 over Q, it might still get rank 1 or higher rank over your real quadratic field. So you could still have infinitely many exceptions. And so for this reason, one wants to do also, there's a 3-7 modularity switch. Sorry, 3. And this is more subtle because the associated curve is now a twist of the Klein-Quartic. So if you look at the corresponding twist of the modular curve with full level 7, this is going to be a twist of the Klein-Quartic, which is genus 3. So it's harder to produce the desired rational points there, but one can still do it using, again, Hilbert irreducibility. One can cook up an argument. That's what they do, Freitas, Lehon, and Sixet. And another thing to say is sort of, over Q, handling exceptions is relatively easy. Over a real quadratic field, handling exceptions is more involved. You have to consider modular curves with small level at 3, at 5, and at 7, and you have to understand all their rational points. So for all exceptions, let me just say that exceptions are classified by curves of genus greater than 1. So by Faltings' theorem, they have finitely many points over that particular real quadratic field. But in practice, these curves can get quite complicated, and sort of showing that all their points are modular is, more difficult. So one uses various tricks. For instance, one can use the fact that if you know the J invariant is rational, then some twist of the elliptic curve is a rational elliptic curve, and you know modularity for that. Or if you have a curve that's sort of isogenous to all its twists, then it's a Q curve, and that's also something that's known to be modular. So there are, and of course in the CM case, you know modularity and so on. So there are these various tricks that one uses, but overall it's a more involved argument. Okay. So now I want to talk about the imaginary quadratic case. And before I tell you what we can show for now, sorry about this. I want to just mention that there's a qualitative difference. So if F is an imaginary quadratic field.
Are you writing something, Anna? Because
yes,
on this side, it's frozen.
Oh, I'm sorry about this.
And try and move it now.
I am.
Oh, that's okay.
That's okay now. Okay, yeah, great.
Thanks.
You can see it. Okay, good. So F is an imaginary quadratic field. There's a qualitative difference that comes from the fact that we want to look inside, right, for systems of Hecke eigenvalues. Say H star, where star is really going to be just 1 or 2, of some locally symmetric space with some level, where now this X gamma, so gamma is a congruent subgroup again inside SL2OF. But X gamma is one of these Bianchi manifolds. So it's a quotient of hyperbolic 3 space by gamma. And these do not have an algebraic structure in any natural way. And so you don't directly have access to the étale cohomology of these spaces. And so one big obstruction when you just first consider this question is that sort of the connection between systems of Hecke eigenvalues, or rather, automorphic forms in this setting, and Galois representations is more subtle. So I guess you still have, if I have a system of Hecke eigenvalues or an automorphic representation here, you still have Galois representations. But this is more subtle, and in particular, understanding the p-adic Hodge theoretic properties of these Galois representations when you restrict to the decomposition group at P is more subtle. And I guess in full generality over CM fields, let me just say, so for GLN over F, where F is a CM field, this is work of Harris, Land, Taylor, and Thorne, and also Schulze with a different method. And Schulze actually also handles torsion in the cohomology of the locally symmetric spaces that you see for GLN over CM field. And so this is an important difference from the real quadratic case. And so let me tell you what result we have for now. So joint work with James Newton, as I mentioned. So let F be imaginary quadratic, and E an elliptic curve over F. And we're going to assume that it's non-CM. Otherwise, its associated Galois representation would be reducible. And so you can understand that case. And we're also going to put a hypothesis, which is a large image hypothesis. So for sort of P or 3, P equals 3 or 5. So either one of them works. We want to assume that the action of the absolute Galois group of F zeta P on, I guess, EP is absolutely irreducible. So this is, a precise large image assumption that we need to assume mod 3 or mod 5. And then if this hypothesis is also satisfied, then, so maybe say here such that this, then E is modular. Okay, so I can make first maybe a few remarks about this theorem and what else, sort of what was known before, and sort of what's the sort of most that we hope to prove at the moment. And then I'll go back through the steps in the modularity argument and tell you what changes there are. So well, one thing is, so these curves are known to be potentially modular. So this is work of Boxer, Caligari, G. Piloni, and also it follows from the 10 author paper. Maybe I won't. So up to passing to some finite CM extension of F, you do know that all these elliptic curves are known to be modular. And this is, well, alternatively, the 10 author paper. The second thing is that as in theorems A and B, one can sort of try to understand exceptions. So maybe the first thing to say is that this hypothesis H is satisfied by 100% of elliptic curves over a fixed imaginary quadratic field. So if F is fixed, then 100% of elliptic curves satisfy this hypothesis. And we can also hope to understand some exceptions. So, for example, I guess we would hope that whenever, so if F is such that X naught 15 over F has more del V rank 0, then sort of we hope to prove modularity of all elliptic curves over that F. And that's just looking at exceptions, which are modular curves with small level at 3 and at 5, and sort of understanding their imaginary quadratic points. And somehow you can show that there are really only finitely many exceptions if this particular elliptic curve has more del V rank 0 over F. So that's sort of the big obstruction, the source where you have sort of infinitely many elliptic curves that we cannot yet understand. So this would apply, for instance, to the Gaussian numbers, or Q adjoint square root minus 2, or Q adjoint square root minus 3. There's a conjecture of Goldfeld that predicts that 50% of imaginary quadratic fields satisfy this condition, that say any particular elliptic curve would have rank 0 over 50% of quadratic fields. Okay, and another important thing is that the modularity results, the residual modularity results of Allen-Khare and Thorne are extremely important for us. So they proved residual modularity for Galois representations over CM fields, in particular over imaginary quadratic fields. These are crucial for us. And I should say there's also so they already proved the modularity of a positive proportion of elliptic curves over imaginary quadratic fields by combining their residual modularity results with an ordinary modularity lifting. And there was recently a paper on the archive of Dmitry Whitmore, who also proved modularity of a positive proportion of such elliptic curves. So both he did it and also Allen-Khare and Thorne. The difference is that Whitmore is sort of refining the methods introduced by Boxer, Caligari, G. Piloni. And for that reason, sort of their results sort of even apply to elliptic curves over arbitrary quadratic extensions of totally real fields. So they even go beyond the CM assumption. Okay, so that's maybe I'm done with remarks, and now I want to go back. Is this, yeah, this is moving. I want to go back to the 4 steps and sort of highlight what needs to be done differently. So I guess the key thing in proving modularity lifting theorems, I'll write in red sort of the differences in the imaginary quadratic case, is that you also sort of want to use the techniques and ideas introduced by Caligari and Garrity. And roughly the idea is that when you work beyond the setting of Shimura varieties, when you have locally symmetric spaces that don't have an algebraic structure, you have to consider the torsion in their cohomology. So you have to sort of work with cohomology, say with integral or maybe torsion coefficients. And when you apply the Taylor-Wiles patching, you're not patching sort of one cohomology group or one space of automorphic forms, but you're really patching complexes. And sort of one can get more technical about this, but roughly we need to use the Caligari-Garrity patching method when one patches complexes. And at the same time, at P, we want to work with sort of the method that Kissin introduced, where you're working over a local deformation ring and specifically over a Barsotti-Tate deformation ring. And the nice thing is that this has a very nice geometry. And there will be sort of 2 components. One of them is classifies crystalline lifts of your residual Galois representation that are not ordinary, and one of them parameterizes lifts that are ordinary, crystalline lifts that are ordinary. And somehow the fact that you only have these 2 components is crucial for proving a modularity lifting theorem in this setting. The residual modularity. So both step 2 and step 3, both of these are provided, as I mentioned before, by this paper of Allen-Khare Thorne, which is from 2019. So they prove very strong residual modularity results, mod 3 and mod 5. And there's one subtlety here, which is that they don't use the Langland's tunnel theorem because it's hard to produce congruences to automorphic forms of parallel weight 2 in this setting where you're working with locally symmetric spaces that don't have an algebraic structure. And instead, what they do is they prove a sort of residual modularity mod 2, and then they do a 2-3 and a 2-5 switch to get the stronger results, mod 3 and mod 5. And I guess, let's see, in terms of understanding exceptions, maybe the thing to say is that here sort of we look at modular curves with small level at 3 and at 5, and we weren't able for now to do a 3-7, say, modularity switch. And that's why sort of we can't right now say that, yeah, we know how to prove modularity of all elliptic curves over imaginary quadratic fields. And that's sort of, if you were able to do the 3-7 switch, then sort of you would work with a modular curve, say x0 15, but you'd add some small level at 7, and then you could, you would be on a higher genus modular curve. Okay, so for my remaining time, I guess there are sort of two things that I want to say. One is, what's the key new idea for doing step 1? Which is, so sort of the key new ingredient is this modularity lifting theorem. So is in step 1, this sort of Kissen style modularity lifting theorem in the Barsotti-Tate case, and especially sort of for crystalline non-ordinary Galois representations, right? So sort of that's the thing that was not available in 2019 when, say, Allen-Khare Thorne proved their residual modularity results. And for doing this, the key obstruction was proving a local global compatibility. So more precisely, sort of really the key ingredient is a local global compatibility result for the Galois representations constructed by Schulze. This is needed so that you know that sort of all the families that you're constructing when you're doing patching really live over the right local Galois deformation ring, the one that has, this really nice geometry. So the key ingredient is to sort of really understand the p-adic Hodge theoretic properties of these Galois representations at P. So I want to expand on this for the remaining part of my talk. Maybe if there is time at the end, I maybe would also like to tell you how to deal with one exceptional case, just to get a sense for what's involved in that. But I think I'll prioritize the local global compatibility stuff, and the sort of, that's more, I don't know, theoretical, and also sort of uses p-adic Hodge theory. So for this, I need to introduce some notation. So let's say that G is the restriction of scalars from F to Q of GLN. And so this local global compatibility result will work really for GLN over a CM field. So F is assumed to be a CM field. And for technical reasons, it's actually, we want to assume that this is not imaginary quadratic. So it is, and you can put yourself in a situation, even if you start out with an imaginary quadratic field, using base change, you can put yourself in a situation where you go to some CM field that's still solvable, and so you can do things over there. Okay, and then xk, let's say k inside G, GLN, yeah. Inside the finite adels, so putting all of these things together, you can construct a locally symmetric space, which doesn't have an algebraic structure. So it's really sort of, yeah, higher dimensional case, but sort of behaves like these Bianchi manifolds. And then you want to also have a local system on this locally symmetric space that will encode the weight of the automorphic representations you're looking at, or, conjecturally of the Galois representations that would be associated to it. So I would take lambda to be a highest weight for G. And this gives you some algebraic representation. And let me just skip ahead and say, ultimately, it gives rise to a local system on xk. And this is going to be of, say, O modules, where O is the ring of integers inside some finite extension of QP, which is assumed to be large enough so that your representation and your local system are all defined over it. And basically, yeah, you use the action of the sort of P part of this level K to descend some trivial local system to this locally symmetric space xk to get something interesting. And then sort of on the automorphic side, you have the cohomology of such a locally symmetric space with coefficients in lambda. And this has an action of a Hecke algebra that's sort of is the restricted product of spherical Hecke algebras at good primes. And we're going to define maybe TK lambda to be the faithful quotient of this algebra that acts on this cohomology. So this is going to be the image of T2 endomorphisms of such, these cohomology groups. Maybe I want to take the direct sum over all the degrees. And then you want to look at a maximal ideal of this faithful quotient, which means this will be a maximal ideal in the support of one of these cohomology groups. And so this will be essentially a system of Hecke eigenvalues that contributes. And it could be, something that corresponds to torsion, right? Something that doesn't actually, that disappears after you invert P. But nevertheless, to something like this, there is an associated representation, rho m bar, which is valued. It's a residual representation. Here, F is sort of, again, large enough. So it's really is some finite extension of FP assumed large enough. Right, there is a Galois representation that is associated to this system of Hecke eigenvalues by work of Scholze. And if you assume that this is absolutely irreducible, then there is also a lift of this to characteristic 0. So this is going to be valued in the completion of our faithful quotient of the Hecke algebra at the maximal ideal M. And theoretically, yeah, okay, so to be precise, we only know this up to some nilpotent ideal. But this isn't very important, so I won't talk about it much. It's not very important for what we're doing, for trying to prove a modularity lifting theorem. So the kind of result that one needs is the following. So let V dividing P be a prime of our CM field. And let's assume that our level K is of the form some level away from V and some level at V, where the level at V is GLN of OFV. So it's full level. This is the case where, so you're assuming that your system of Hecke eigenvalues contributes to the cohomology of a locally symmetric space, where the level FV is GLN OFV. And in this setting, you would expect that your associated Galois representation, rho m, is crystalline. Like if you had a good notion of crystalline, I guess at least after inverting P, for instance, you would expect it to be crystalline. So more precisely, what you expect, and this is something that's formulated maybe for GL2, it's formulated in a paper of G and Newton, this conjecture. So you have your Hecke algebra. So faithful quotient completed at M and modulo this nilpotent ideal I. There's a universal deformation ring for the residual representation rho m bar. You're looking at deformations that are unramified outside a fixed finite set of primes. And you can define this deformation ring, and the existence of the lift rho m gives you a map like this. And sort of this map is key for proving modularity lifting results and for studying, for implementing this patching method. So this follows from the existence of rho m. There is a map, just by restriction to the decomposition group at V, there is a map from the local. So this is the unrestricted local deformation ring, framed local deformation ring for rho m bar G, restricted to GFV. And this has a quotient that was constructed by Kissen, which only sees those deformations, which in characteristic 0 only sees those deformations that are crystalline and with Hodge-Tate weights, determined by this vector lambda V. There's a formula that involves some shift, but with Hodge-Tate weights by this. So this is the quotient where sort of the characteristic 0 points, let's say E primed valued points, are crystalline with Hodge-Tate weights determined by lambda V. So, your lambda is really a vector that's indexed by various embeddings of F into C and up to having an isomorphism with QP bar. You can choose those embeddings that correspond to the prime V dividing P, and you look at just the subset of those vectors. Anyway, so you have a nice deformation ring like this, and this is whenever E prime over E is finite. And so the conjecture is that this map here factors this way. And that would tell you that sort of even when you don't have a good notion in integral p-adic Hodge theory for describing the representation rho m, sort of this tells you that sort of rho m restricted to GFV looks as you expect it to look, which would be crystalline with Hodge-Tate weights determined by lambda V. In the Fontaine-Lafay case, you do have a good notion in integral p-adic Hodge theory. So you can just say, in that case, you expect the representation to be Fontaine-Lefay at phi. But more generally, the way that you want to formulate it is to just say that it factors through the right deformation ring. And this is also what you need for modularity lifting. And I should say that there is an alternative. So this is a deformation ring constructed by Kisin, but there is also an alternative definition, an alternative, say, construction of this due to Tong Liu, who describes the mod p to the n points of this deformation ring are those that admit lifts to characteristic 0.
We don't see anything.
Oh,
what you're writing just now.
Just now. Now you see it?
Yes.
Yeah. Okay, great.
Yes.
Maybe best to not to worry about it. Right. Thank you for letting me know. So are those that admit lifts to characteristic 0 that are crystalline and with the right Hodge-Tate weights? And so what James and I do is we prove this conjecture under, a few additional technical assumptions that don't cause problems for applications to this theorem C. And the way that we do it is we construct really a sort of a characteristic 0 lift of rho m restricted to GFV that has sort of the right properties. So again, crystalline and with Hodge-Tate weights determined by lambda. And so the question is, again, to look at these Galois representations constructed by Schulze.
Again,
you don't see anything.
Writing doesn't appear.
Sorry. Well, I'm almost at the end, so maybe that has the right property. So maybe for now, That's okay. Right. So the key thing is that we use basically some of these techniques that were introduced in the 10 author paper, but we combine them with the theory of p ordinary parts. So sort of the key ingredient, now I think you can see it, and this is really the last, is theory of p ordinary parts, where p is now a parabolic inside G tilde, where G tilde is roughly something like UNN over F plus. And this has Levy quotient, our group G that we're interested in. And so the idea is, in constructing the Galois representations to begin with, is to look at the locally symmetric space for G and see that it contributes to the cohomology of the locally symmetric space for P, which in turn shows up as a boundary component for the locally symmetric space for G tilde, which is actually a Shimura variety. So sort of the relationship between our group G, which is essentially GLN over F, and this larger unitary group over F plus is key. And for us, the key idea that we use for local global compatibility is we work with p ordinary parts at this prime V where we're trying to understand things. And so that means that we're really constructing a 2n dimensional representation. Rho m bar, rho m tilde, which is 2n dimensional, and which, when you restrict it to GFV, looks like this, where these are n by n blocks. And one of these blocks is a characteristic zero lift of the Galois representation rho m restricted to GFV. And it's on one of these blocks, we're able to check that we have the right properties. All right, so you want to go to lunch, so I'll stop here. Thank you very much for your attention.
Still, we may have time for one question. Have we one? Yes.
So if I understand correctly, so the local system, you need to choose some lattice is that correct? And what lattice do you choose, or you just prove for all the lattices?
I think that the proof works for all the lattices, but we work with the dual Weil module, I think is what it's called. So I don't think there's anything special about the lattice, but I agree, yeah, that you could imagine that there is a difference.
I see.
But the specific one that we work with is, yeah, this dual Weil module. So you take the algebraic induction and you evaluate it on O, which is your ring of coefficients.
Thank you.
Is there any other question or comments, or on Zoom something? No, in this case, we thank you very much indeed.
Thank you.